on this episode of Science. Hello everyone and welcome to Science. My name's Nate Macon and I'm the physics teacher here at Skyview High School. We have a great show for you today and it's all about waves. Now when you think of waves, you probably think about this. But waves are all around us. At school, even in traffic. So how are those other things waves? And why should we care? Well today, we're going to find out. A textbook will tell you that you can define a wave by the motion of the object that moves to produce the wave. But I think it's easier to understand this concept and the concept of waves by using everybody's favorite Christmas gift from 1966. The Slinky. Now I'm going to need some help operating this complex piece of scientific equipment, and that's why I'm going to need my physics team. Who's that guy?
Yeah, that's our fan guy. He's the best.
Yeah, I can't believe he works for tacos.
Tacos. Right. Slinkies. We're going to use slinkies to show you how waves work. In nature, there are two kinds of waves, transverse and longitudinal. Transverse waves are much easier to see, so for now let's stick to those. Just know that everything we say about transverse waves applies to longitudinal waves as well. When the physics team uses our slinky to make a transverse wave, notice how the motion of Will's hand is perpendicular to the direction the wave is actually traveling. He is moving his hand back and forth sideways, but the wave is moving away from his body. Boom! Transverse wave. If Will uses more physical energy by shaking his hand faster, notice that the number of waves created increases. This is called the frequency, and it tells us how many waves are created in a set amount of time. To measure the frequency, we take the number of waves and divide it by the amount of time it took to make them. That unit is called a Hertz. So if Will creates 20 waves in 10 seconds, the frequency at which the wave is created is 2 Hertz. In addition to frequency, we can also measure wavelength. Now, to measure wavelength, we need to create what's called a standing wave, where we send waves down on one side of the slinky and allow them to reflect back upon themselves. Lauren creates a standing wave by shaking the slinky quickly. Notice that as the wave reflects back upon itself, we can see different portions of the slinky doing the same thing at the same time. We can see those peaks and valleys by pressing pause. This is a standing wave, frozen in time. We can now determine the wavelength by measuring the distance between the peaks of two waves. This is the length of just under 1 meter. In science, the symbol for wavelength is lambda. So we've measured frequency and wavelength. But what about wave speed? If we shake that slinky as hard as we can, do you think the speed will change? Will the waves get faster? Think it over while we take a quick coffee break. To begin with, let's make a very lazy wave. Will, give it a 3 out of 10 effort, and let's see the wavelength. Okay, now let's step it up to a 7 out of 10 effort, and see what our wavelength looks like. All right, 10 out of 10 effort. Again, look at the wavelength. What happened? Did you notice anything? As our energy increased, so did the frequency. And as the frequency increased, our waves got shorter and shorter and shorter. You can really see it when we show the three next to one another. The more we shake the slinky, the smaller and more frequent the waves. But the wave speed didn't change. Here's a simple formula. Lambda, or wavelength, multiplied by the frequency, measured in hertz, is going to equal the wave speed, measured in meters per second. It shows us the relationship between wavelength, frequency, and wave speed by calculating how far the wave moved in a set period of time. Think of it like this. It's the same way we measured speed when we drive. The 70-mile-an-hour speed limit on the freeway tells us exactly how far we can legally go in a set amount of time. That is unless you're Burt Reynolds. You can drive as fast as you want, whenever you want. So the slinkies are fun, and if you have a slinky at home, feel free to try the wave experiment with your slinky. But there's more fun you can have just by changing the medium.
Like the pitch of your voice.
For this experiment, you're going to need a helium-filled balloon and your parents' permission.
Did you know that the speed of sound through helium is 3 times faster than in air?
And when you inhale helium, you're changing the medium with which you talk.
Now my pitch is 3 times as high.
Yeah, that was pretty good, but you shouldn't do this too much.
So here's today's famous scientist.
Today's famous scientist is Louis de Broglie. If you're saying to yourself, I never heard of this guy, well, you should have. His discoveries in matter, the very essence of our universe, put him right up there with Max Planck and Albert Einstein. You may have heard of them. Like most guys named Louis, Louis Vuitton, Louis Braille, Louis Pasteur, and King Louis XIV. He was French, and boy how. His full name is Louis Victor Pierre Raymond, the 7th Duc de Broglie. It doesn't get much more French than that. He was born into nobility in 1892 and used that advantage to focus on academics. His first degree was in history, and he may have continued down that path if he hadn't become a part of history. World War I broke out, and as a soldier in the French army, he was assigned to radio communications, working out of the Eiffel Tower. That led him, eventually, to wave mechanics. Whoa, not so fast, Keanu. Louis was hanging 10 on much smaller waves. De Broglie extended Einstein's theory that light waves contain particles, like the photon, which are part of the wave that carries them. De Broglie said that all matter has traits of both particles and waves. That was a big change from previous theories, which insisted that particles and waves were separate from each other. Albert Einstein himself endorsed de Broglie's work. In 1929, the rest of the world agreed, as de Broglie won the Nobel Prize in Physics. The results of his theory and the following experiments are the foundation for the development of quantum mechanics, a very important field of study that is helping us determine the origins of the entire universe. I am not kidding. Just ask the gentleman at the Large Hadron Collider outside of Geneva, Switzerland. De Broglie is regarded as the father of wave mechanics, and a man who best demonstrated how our world works on a very, very small scale. The atomic scale. For most of his later years, he taught at the Sorbonne. It's just a couple of miles from where he spent his service during the war. From that distance, he could see the lights of the Eiffel Tower, knowing that his ideas help us better understand how those lights shine into the night sky.
Wow, wasn't that interesting? So what we've got here is your basic Rubens tube. Now we alluded to it earlier, but I want to take you through a couple of things. Now what the students have done here is we've basically taken about a 4-foot section of pipe. We've drilled a bunch of holes through the top of it, about a quarter of an inch past each other. On one end, we've got a PVC portion that's threaded so we can screw it in, and we've attached that to the pipe with some high temperature caulk, anything that you could use for a fireplace. That is our connection to our propane tank and our safety valve. Very important. Now on the other end, we don't have it capped, and instead of having a cap, if you were to make a gas burner, instead of having a cap, we've got a speaker. And the speaker is attached with, if you can see this, with basically just a rubber glove. Now the speaker at this end is really important because it is going to vibrate our medium, which is the propane. Now, before it's fire time, we need to talk about the safety precautions here with the Rubens tube. A few precautions. One, we've got a safety valve hooked up to our propane tank. And that safety valve, we can shut off the propane in case the flames get too large. Second, we've got a fire extinguisher. And third, we're going to keep everybody back about 6 feet from the propane and the open flames. Now, the open flames won't be that big, but we just want to take every single precaution because, you know, anytime you do a scientific experiment, you need to take safety into account. And I think we've done a pretty good job here. First, let's take the propane tank away from the flames and place it on the floor. And now, it's fire time. Lights! So right now, all we've just got is some flames. And it's burning just like any gas grill would burn. But the speaker here, when Lauren plays a tone, is going to create a very, very beautiful standing wave. Now what happens in the tube is that we get some very, very defined places where we either have compressions of propane or decompressions of propane. So Lauren, why don't we play a tone? So you can notice, why don't we crank it up a little bit? So you can notice that as she changes the frequency, we're getting smaller and smaller wavelengths. Now let's think about compressions and decompressions of air. Anytime we have a compression, that means there's a lot of molecules all in one spot. And because there's a lot of molecules all in one spot, we're going to have a lot of air coming out of certain holes. And that's where we get these very, very, very nice peaks. Now when we have a decompression, we end up having very, very small flames because there aren't as many molecules. So this speaker is creating a very nice standing wave. And that standing wave is reflecting at one end of the Rubens tube and coming back on itself, just like we saw with the Slinky. Now if Lauren, just like with the Slinky, plays a higher frequency, we should see our wavelength decrease and get smaller and smaller and smaller. Go back down just a little bit more, there we go. So we can measure wavelength of these waves given by our propane from peak to peak or from valley to valley. And then we can determine the actual speed of the wave in the propane if we wanted to. While listening to tones and seeing the fire make our beautiful transverse waves is great, let's try something a little bit more interesting. Hit it, Lauren. So here's the point. By knowing about waves, we can solve a lot of real-world problems. This is just kind of fun. But since we know about waves, we know about how they behave in different materials, we can make contact lenses, glasses, speakers, headphones that cancel other noises. It's actually pretty beautiful what we can do by knowing about waves. Let's check the old science mailbag. Our first email comes from Jack, who asks, Mr. Macon, in the last episode you shot a monkey with your air cannon. I want to make sure that the monkey's still doing okay. Thanks, Jack, for your email. If you didn't see, our last episode was all about gravity, and to show that all objects fall at the same rate. We dropped a green stuffed monkey named Chattels from this balcony at Skyview, and fired a tennis ball at him with an air cannon. The ball fell at the same rate as our monkey, which meant Chattels got whacked a lot. Jack, I'd like to take this opportunity to personally assure you that Chattels is doing just fine. We sent him to a farm, out in the country. He's running, laughing, and playing with all the other stuffed monkeys and stuffed animals. Doesn't that sound nice? If you want to get your question on air, email us at scienceshow@vansd.org. Now, we only scratched the surface about waves, but if you're interested in learning more, join us for some science extra credit. It's a web exclusive at youtube.com/vansdtv. Well, that about does it for us. And I'd like to... Man, something smells really good. Something smells like it's cooking. I'm Nate Macon.